Question 20, June 2024. This question is Group 7 Chemistry. This question is about elements in the periodic table. Chlorine has many uses. Chlorine is used to treat water in large-scale water treatment plants. Suggest why chlorine is added to water in large-scale water treatment plants. The simple idea here is that chlorine, it kills bacteria. It kills bacteria or microbes, or it sterilizes the water. That's why chlorine is used. They could ask you, what's the disadvantage of using chlorine in water? This idea that chlorine is actually toxic. That's the downside. It says seawater contains bromide ions. Chlorine is used to extract bromine from seawater. Construct the ionic equation for this reaction. Explain why chlorine is suitable for this extraction of bromine, but iodine is not. So first of all, when we get chlorine and we react it with seawater, which contains bromide ions, what happens is chlorine gains electrons to become chloride, and bromide loses electrons to become bromine. And we balance accordingly. And the explanation for this, the simple idea is that chlorine, why does it react? Chlorine is more reactive than bromine. That's why this reaction happens. And it's asking why, but extraction of bromine is suitable. Why is chlorine suitable, but iodine is not? Chlorine is more reactive than bromine, but iodine is less reactive than bromine. You must say both points. See here, it's very easy to miss the last mark. You could say chlorine is more reactive, but you've missed out the mark because you've not read the last bit here, which I nearly did now. Next question is looking at the multi-step mechanisms for rate equations. It says fluorine reacts with nitrogen dioxide, NO2, to form nitrile fluoride. It's shown in the equation here. The mechanism for this reaction involves how many steps? It involves 2 steps. Step 1 is the slow step, and step 2 is the fast step. They've given you the fast step here, and you have the overall equation here. So, can you see that the slow step, how do we extract the slow step, or step 1? You see fluorine, which is not in the fast step, must be reacting in the first step. Notice there's one NO2 in step 2. That means the other NO2 must have reacted in the step 1, NO2. This would give you one of these NO2F. NO2F. We look at the products to give us a hint what's been made. And you see in this equation, a fluorine atom is still left over. That fluorine atom then goes into the fast step to react with the other NO2 molecule to give you the other NO2F, which confirms what confirms this is correct is that if you combine step 1 and step 2, it gives you the overall equation. So I can quickly show you this. And you see whatever's on both sides cancels out, F and F. So you end up with F2 plus 2NO2 gives you 2NO2F. The rate equation would be, you can see in the rate equation, in the slow step, step 1, rate will be equal to the K constant. F2 is first order because there's only one F2 reacting, and NO2 is also first order because there's only one molecule reacting. That's that. Let's move on. In this question, again, the table shows the melting points. So we're dealing here with melting points of some elements in period 3. Explain the melting points in terms of bonding and structure. You see, with aluminium, bonding and structure, generally, you want to think about what particles are involved in the structure. What is the force of attraction between those particles in the structure? And yeah, that's the main sort of ideas. So if you look at aluminium, what bonding is present in aluminium? It's metallic bonding. What is metallic bonding? It's electrostatic attraction. Electrostatic means opposite charge, oppositely charged, of electrostatic attraction between positive metal ions and delocalized electrons. Now you see the metallic bonding is strong force of attraction, which requires a lot of energy to break. These are the main points for aluminium. For silicon, what you've got is I should have mentioned here, metallic bonding is a giant structure, giant, because you've got a sort of a continuous arrangement of the particles in its structure. Silicon is a giant covalent structure. Giant covalent structure. Now you see in silicon, like with diamond, silicon forms 4 covalent bonds. What are covalent bonds? Sharing of a pair of electrons between atoms. Which again, well, in this case, which require, because the melting point is higher, most energy to break. Generally speaking, ionic, metallic, and giant covalent requires a lot of energy to break these bonds. And then you see we've got the last two, P4 and S8. P4 and S8. Phosphorus hangs around in 4s, sulfur in 8s. You see, these are known as simple molecular structures. Remember, silicon was a giant molecular or giant covalent structure. These are simple molecular structures. There's covalent bonding within the molecule between the atoms. However, there are weak London forces between molecules which are easy to overcome. So less energy needed to overcome. That's why these two have the lowest. Now, you see, why is S8? S8 has a higher melting point than P4, as, again, we've seen this many times in past exam paper questions, as S8 has more electrons, and those more electrons cause there to be more London forces, which requires more energy needed to overcome these intermolecular forces. That is that, ladies and gentlemen, and I'll see you soon.